Good morning, ladies and gentlemen, boys and girls, everyone out there. We're about a minute away from getting started here. Hope everyone's having a good morning. All right, let's get this show on the road. My name is Stephen Loftus-Mercer. I work for National Instruments and LabVIEW R&D. With me today is Alan C. Smith, Certified LabVIEW Architect, and running the Q&A is Darren Nattinger, also of LabVIEW R&D. You can see our respective handles there on the title slide. Some of you know me as Aristos Queue over in the forums. Alan is Just ACS. And today, after many years, we are finally bringing interfaces into LabVIEW. And we're going to be discussing the brand new LabVIEW 2020, which is available. Darren has put a link where you can download that into the Q&A section. And when I finish my section on the introduction, Alan will be talking to us about how interfaces affect the actor framework. Yes?
Yes.
All right. In that case, let's go ahead and get started. We'll flip over to slides here. Now, my presentation, this is a brand new tech. I can't see you. We had to string a lot of things together, and I thought I would start with a show of how I was able to use interfaces for this new technology. So here we go. So I have my presentation, some PowerPoint, some LabVIEW. It's all nice together, and I need to get it out to my customers. So I need a method, watch presentation, and I had to think a long time about how to code this up. So I need to know which class this watch presentation method goes with. So my first attempt was, well, I just mocked it up and I said, okay, run LabVIEW object into it. I know I'm going to need something there, but now I need to think about what really should I be passing in here. I mean, jack devices, they're not going to be watching my presentation. Bowling balls don't even have eyes. All of these are things that could be types of LabVIEW objects. Frogs at least have ears. They can watch the presentation. They're a living creature, but that's still probably a little too broad. Let me think about intro, ladies and gentlemen, boys and, oh, okay. Maybe I could have classes for lady and gentleman, and then I could build an array of those, and wait, there's no parent class, so my output type is still LabVIEW object. Oh, I can fix that. Let's see, I'll create a class human, lady, gentleman, come off of that, and there, now my output type is human. Humans can watch my presentation. That seems reasonable, but there's a couple problems here, because that whole child thing, I mean, an actual child class, that's going to have a lot of duplicated code. Maybe I redo it. Okay, human, female, male, lady, gentleman, girl, boy. Okay, good. Now, wait, we're in the 21st century. We've got non-binary, asexual, transgender. And you know what? Honestly, this whole thing makes me start to wonder whether I even have the right classification system, because is any of this biology at all relevant to my presentation? I mean, that might be the actual implementation that has been used, but none of that is necessarily relevant to watch presentation. Okay, back to the beginning. Knows English. Because, I mean, let's say we had a DAC device that actually could understand English, which would be a great technology from National Instruments, because I could yell at the hardware and maybe it would understand for once. If that was the case, then it could watch my presentation, and any human who knows English could watch my presentation. So anyone who knows English. So really, that's what I'm talking to, is an English audience. And so I could have an array of knowers of English, and so watch English presentation. That's good. And so I could have all of my customers. I could create a class for each customer, implement them properly. You know, you guys, normally I would have an audience for this, but now it's all these individuals are just virtual individuals. We'll call them VIs going forward. Oh wait, that might be confusing. But I've got all these customers who speak English. They'll be able to watch the presentation. Y si tengo una presentación en español, es posible. Then I could create Knows Spanish con its own. Fabiola. I forgot. Fabiola can speak both English and Spanish. I can't have this inheritance tree. I suppose I could put Fabiola in a class by herself. I mean, that would kind of be appropriate if any of you knows Fabiola. But that could lead to a lot of coding, and I really don't know what languages Chris speaks or Steve speaks or anyone else. Re-implementing all that's going to be a problem. And if I put a Fabiola into this array, we're right back to LabVIEW object because there's no common parent. Need a better way. Definitely need a better way to organize this. All right, so I think I'm on the right course with this knows English thing. What I really want is, I've got all these people who are implemented. They're well defined and everything, and maybe one of them is a secret cyborg. I don't care about their implementation detail or how they are actually deriving their functionality. What I care about is that they know English. In addition to whatever they are, they have this interface. They have this behavior of knowing English. And I can build them all together and get an array of knows English out of that. And if one of them knows Spanish, I should be able to put that on the side because that's another separate interface. And I should be able to just add those on to my existing hierarchy and give them functionality. Interfaces. Yeah. See, and that was the big breakthrough. And that's what allowed me to implement the tech that's letting you see all of this today. I re-implemented all of my customers as virtual objects, and I applied appropriate interfaces, and that's what's running right now. You all think you're real people, but as far as I can tell, you're just virtual simulations. I really hope we get over this COVID thing soon. All right. I think I now know how to do my presentation. Welcome, knowers of English. Today, we are going to discuss interfaces in LabVIEW. And what you just saw is a little bit of the mindset that takes you into how interfaces work and why we need them. So in 2006, we introduced LabVIEW classes. And in 2020, classes have to move over and they now share the stage with LabVIEW interfaces. Interfaces are a new type of type. Just as classes are a type of type, they're a wire that you run through, and there's a lot of different classes. There's going to be a lot of different interfaces. They're peers. They're going to work with each other. The new interfaces are going to augment the classes, give them some new abilities. As much as possible, our goal is that your knowledge of classes will lead you to be able to use interfaces and just roll right into this. We'll see if we've managed to do that. So what is an interface type? In a general context, if we talk about a software interface, we have a set of functions that one code module uses to request functionality from another code module. It's anytime you group a block together, sometimes we'll call it an API, an application programming interface. See the interface word? Interface is like this chunk of functions, put them all together, and someone else is going to be calling those to get some functionality done. What we're talking about today is a very specific use of the word interface that is developed in programming, which is a new data type that defines a set of tasks that an object can do without specifying how those tasks must be done. Those of you who are familiar with the concept of an abstract class, this is similar, but it's a little different. Now, some of you have seen my presentations on LabVIEW classes in the past. And for classes in any programming language, we usually talk about three things that make class 1 different from class 2. Identity, state, behavior. The identity is how is it known? What is the name of the class? What's some of the documentation? When I talk about one of these things, what is it? Is it a GPIB device? Is it a DAC device? Is it a VST? Is it a bowling ball? These all have very different identities. State is its internal data. with a little bit of reflection out to the world is like, what modes can this thing be in? And you can have two things that are basically the same identity, but their implementation details are different. They're the states that they move through are different, and therefore they get separated as separate classes. Those are cases when you usually have a common base class. And then we have behavior, which is the list of methods that you can call that cause changes in the state. Now, these are the three parts that we use for figuring out where a class belongs in a class hierarchy. Interfaces come along and they say, look, we would all like to have, ways of compositing classes together better. But to do that, we're going to get rid of state. Interfaces define identity and behavior only. They are a name and a list of functions, but they don't say anything about how do I do this. All right, so an interface is a user-defined data type with encapsulation and inheritance. That's just like a class. An interface has all the parts of a class except the private data control and the call parent class method node. It has some inheritance, but you can't call it to the methods because that would be defining how things get done. And classes inherit methods from interfaces and then provide their own implementations. This is the same thing that you've experienced with overloading and dynamic dispatch. Now, over on the side here, we have our first picture of LabVIEW, and you can see there's what an interface looks like in the project tree. I've grayed out the file extension. We'll discuss that in a little bit. But this is just, getting you started. All right, and you can see it looks an awful lot like a class, but no private data control. This is the iconography. So we've used a cube as a class. We needed an icon that meant a thing. Well, a box is a pretty abstract thing. We thought about a sphere and a lot of other things. We went with a class. And eventually we had abstract classes, the ones that you never intend to instantiate on the diagram that have the must override methods. And those we use the wireframe cube because it's like all the parts are sketched out, but the internals haven't been filled in. Well, an interface, in addition to being a nice visual pun in English, because we talk about faces of a cube, the interface really is just the surfaces. There's nothing on the interior. There's no structure to it. It's just the parts of the cube that the outside world could touch. And so we went with that as our logical derived icon. Okay, so we have a fully functional class, but we ripped out the private data. So we took out the part that really makes things useful. So why would a customer ever want that? Why did we spend all these years building something that looks like a crippled class? Well, the reason is because there's a problem with inheritance. Yeah. Now I thought about how to explain this to you, and I kept coming back and coming up with different designs, and I needed something that was physical, that people could relate to, but wasn't specific to any one domain. And I kept coming back to the cube itself. Now, all of you always see the front side of LabVIEW classes because you never get to see the back side. Well, when we build these class objects, there's always a welding line on the back because we put all the private data in, we seal it up and weld it on the back. This is a joke. But we've joked about sealing these things together. But I had this as an inspiration is, okay, well, let's say I have a box and I want to open it. And I'm going to represent that in a piece of software. Okay, so I have an object box and it has a method open, and I need to pass into it a tool that is going to be used to open that box. Okay, this is a metaphor we can work with. Well, I have a bunch of tools. You can walk out in the garage. Things for turning screws and pounding in nails, all of this. Well, which ones can I use to open my box? Well, here's my class hierarchy. And when I first started, I said, well, I can group these together, and I've got a bunch of rotating tools, and I've got a bunch of pounding tools, and I got a bunch of prying tools. And so I put the appropriate methods on the parent class, and they all come off of a base tool class, which is this hyper generic thing which has just pretty common methods that everybody has. And if I look at my hierarchy, I'm like, oh, there's the pry method. So I can write a prying tool, and that can any tool that I can stick into that crack and wedge open, that can be used to open my box. So right now that would be the crowbar or the pry bar and the claw. Okay, this is good. But there's a secret if you're, woodworker and everything. The tools sometimes have dual uses. So right now I can pick the pry bar or the claw. I can choose between them, and I'll get the common parent class. So right here, this will be my prying tool. That works. What if I want to pry it open with the nailer? So if I take that hammer, you see the back edge of it, it can stick in, and you usually use it for pulling up nails, but it works really well for prying up over other things. He's got a good stiff shaft on it, and everything works out really nice. And so it can pry things open. And it would, if it's the only tool I've got, because somebody has borrowed my pry bar, the nailer would work and I could use it to try and get the cube open. But if I try to wire that, it's not a prying tool. I'm going to get a broken wire. That's not going to make anybody happy. Now, there's another secret in here. My father, would not want me to tell you this, but secretly flathead screwdrivers can be used to pry things open. You just put that in. It works great on paint cans and stuff, but you can use it for a lot of other things. And sometimes when you're about a teenager, you have to go to your father and say, Dad, yeah, your really nice flathead screwdriver that maybe doesn't have a head on it anymore because you kind of used it as a pry bar. These things happen. And fathers eventually forgive, for which we are grateful. But it is true that you can use a flathead screwdriver as a prying element. Well, it's going to have the same problem as the hammer. I can't. It's not a prying tool. I have to do something to fix that terminal. I need to set the type to be something that will allow prying tools, pounding tools, and rotating tools, or at least some of the pounding tools and some of the rotating tools. Well, I hope everyone knows that going and putting a pry up on tool and allowing all tools to wire in is a really bad idea, right? We've had LabVIEW classes have been out since 2006, and I've given I don't know how many presentations on the fragile base class problem, where you start putting everything on the base class because some subset is supposed to go in there and you can't find any way to get the right subset. And so you end up shoving it up on the base class. And that's what LabVIEW programmers have had to do for a long, long time. And I'm sorry, it pains me when I see this, and sometimes it has been the only thing you've been able to do. There is a better way. All right, we need to set that terminal. We're not going to just put it up on tool, we're going to do something better. So here we go. We are going to introduce a lever interface. We're going to say, hey, lever, you get the pry method. And then we're going to say that the prying tool, that's going to inherit from lever. And it'll override and it'll define the behavior for pry bar and claw. Right. But we're also going to make the flathead and the nailer, just those two classes specifically, inherit from lever. All right. Now at the moment, lever is using some default coloring here that's going to make this hard. So let's go into our property page, and ooh, you almost got to see a little bit of that file extension there. Haha, animation was too fast. We right click on it, we choose properties, we pull up the property page, and we're going to change that over to blue so that going forward things are a little bit more obvious. So just like classes, you can do custom wire appearance. All right, I can now use that lever on any number of classes. So I can take a key. It's a really poor prior, but sometimes everyone's used a key because it's what's in your pocket to pry something up. Okay, so it can be used as a lever. So let's add that to that class. Without interfaces, a house key and a hammer, joining those together, I'm going to get a LabVIEW object because it's the only common class, common type to those two things. And you can't do much with LabVIEW object. I mean, it's useful for generic type things, but it doesn't have many methods. It's pretty much flatten and unflatten and some comparison ops. But with interfaces, oh, look, I could go all the way to LabVIEW object, but there's another common parent along the way, lever. So LabVIEW says, hey, I'll go get the common parent, which is lever. And so we get that blue wire out. And now I can write this code. I can say, okay, choose between the pry bar, the nailer, and the house key. Let's build an array of them and run them in a loop. and we'll keep trying to open the box, and eventually one of them will work, and we'll pop open the class and get it all that lovely, lovely private data. Totally how generic probes work behind the scenes, right? Everybody's like, how do you write a generic probe that can see the private data? Well, I use a prybar. But the code part over here, joking aside, this fundamental aspect of interfaces, the ability to define a set of behaviors and then hand them out to whichever implementing class is going to have that behavior, lets us put an arbitrary subset of our classes into a common framework. In this case, my tools are my classes that I want some special subset of, and my box open is my framework. That is why users want interfaces. It's the first reason that you wanted interfaces. There's a lot of uses for interfaces. There are places where you guys have had to stretch and make things work that you should never have had to stress that hard about. But it's taken us a while to get to the point where we had interfaces in G. And going forward, a lot of workarounds that we've had to do all go away. And speaking as someone who has had 6 months with interfaces in my G code, it's a better world. We can do a lot more abstraction for our hardware, that we aren't trying to create classification hierarchies that are locked in for all time. We can build plugin systems that can be built by third parties without tying them to a specific root class. We can do much better loose coupled messaging so that you can build a client and a server where they don't know about each other and the details of implementation. We can do mock testing where you can create a simulation of a piece of hardware and not have to have the two tied together and distributed somehow because they're dependent on each other. It means you can build the test before you even have the real hardware with a lot simpler interfaces. All these things are going to come into play. And while I'm doing a basic intro presentation today, in the future, we're going to have presentations on all of these things, some from me and some from other customers. So now let's flip over and look at live LabVIEW. So this is LabVIEW 2020, and I'm going to open the basic interfaces project. You can see that path there. Note, I'm in a shipping example. If you go into the examples, object-oriented programming, basic interfaces, this is gone out to you guys. So anybody who's like, well, can I get the code somewhere? If you've downloaded 2020, you already have it. It's been my goal the last few NI weeks to be able to present entirely from LabVIEW, stuff that's already shipped out. Makes my job easier of giving you the code, and it means that you already have it and you can just follow along. So this is my basic example, and here's all the tools that we've just been talking about. The specific tools are in here. I should have put house key in with tools. Hey, look at that. You review the same example for 6 months and it passes through the hands of 5 people, 10 people, an entire presentation test watched this. And now is the first time I noticed that the house key is in the wrong folder. Oh well, moving on. First release 1.0. Here we go. So there's all my tools. These are my base classes for my tools that you saw, and this is my box class. And my box has this open method. And we can take a look at the open method. And the open method says, okay, well, I'll take my box and pass it into the lever. And the lever has this method to pry. And pry, well, let's take a look. This is the lever class's pry. It's got, oh, hey, look, it's got all this code in here. I thought Stephen said that interfaces don't define behavior. Well, they don't. But what they can define is compound operations. And if we look real close here, the core operation is this multiply force. And if I open up multiply force, it's nothing. There's nothing in there because it doesn't know how to do anything. And I've got all these overrides of multiply force. So what I did in the presentation, I just talked about pry because it was easier to win as a first intro. But when I actually got around to the implementation, I was like, I need to have a little bit more substance around this. So I created multiply force, and then I created this default wrapper around this that takes the force and creates a force message and tells you whether or not it opened the box, or what the result is. So okay, that's my prime method, and so there we go. And we come back out. So now open is going to do this, and we cast back, and we're good. So let's go look at our opening the box example. I can set my force in newtons. Everybody go, all my American watchers, go study your SI units. We use metric when we're talking science, and that includes like lengths of my pry bars down here. So I have a house key, a flathead screwdriver, my nailer hammer, my bottle opener, and the Hulk. The Hulk is a pry bar, but I've set its length to be 500 centimeters, which is a gigantic pry bar. But as we know, levers, the longer they are, the more you get a force multiplier on them, back to, elementary school physics and 6 simple machines. So if nothing else opens this box, that's going to open the box. So here's my human force in newtons going in, and my instructions say to probe this wire, and I follow my own instructions. So I'm going to probe this wire, and it's my probe watch window. And so as we see, we're going to go through, we're going to see the actual data type. And I'm going to turn on some execution highlighting so you can watch. And we're going to build up an array here. Now this first array, force applied by house key, 10 times its little tiny length, gives me a total applied force of 50,000. Sorry, 50, not 50,000. And that was not enough. The box is still closed. So we're going to try the next one. Now, if we look at this wire over here, when I put the bottle opener and the Hulk together, I got a prying tool as the type. You see my mouse up there on the context help window? It's a prying tool. Both of those are prying tools, so that's the array. But when I took these three, over here, the only common parent was lever. So I get an array of levers out. So I take my box, we're running through the array of levers, and each time we call open, we get a result, and we see whether it is. All right, so let's run this around the next one. Oh, yeah. So the flathead screwdriver breaks when you apply too much force. This is why woodworkers and fathers get upset when people use their screwdrivers as levers. But you notice how much force that was able to apply. 160 newtons, good amount. See, these things are really useful. And so, but because it broke, the actual force applied is 0. Okay, so that didn't, nope, that didn't open it. The nailer is actually kind of designed for this task. More force, still not quite enough. Bottle opener, that's back to really, it's a little short lever and it's not so good. So still closed, but here comes the Hulk. Force applied, 2,500 newtons, and open, stops the loop, and pops up a string. After 5 attempts, the box is open. Yay. Now, I realize that's not a kind of hardware example that any of you would necessarily write, but you can see where you would start substituting in. This is the thing I'm operating on. This is my, array of sensors that I'm commanding and controlling. This is my machine arm that I'm positioning. This is the system that I'm pulling data out of, and I need, and I'm feeding it different inputs of sensors to use. Over here, these are the things that are going into that framework. These are the swappable parts. The hardware that I've abstracted that I may be using the antique hardware or the newfangled modern system, and the framework doesn't care. I may be using the simulator or the real, and the framework doesn't care. These are the parts that you start thinking about when you start thinking about interfaces. We're going to look at interfaces as a new data type, as an object, but when you're doing the design part of it, it's not the implementation of it, it's just what does it do? And what you're going to find is more and more, wherever you have a logical boundary in your code, like this is going to be something I want to build independently or distribute independently, or work on independently, that's going to be a place where you're like, classes belong there, and at all those boundaries, I should be using interfaces. Now, that's not a hard and fast rule. It's not a requirement, but it's the rule of thumb that I want you all looking at as you start to adopt these into your code. At my module boundaries, think an interface instead of a class. And in a lot of cases, you're going to come up with a better architecture, and one that is far more successful and has various other advantages that we'll get into more detail over the course of the next year as we present more and more information. Now, the coercion rules here are a little interesting, so I'm going to pull this one up. So I have box and lever. Well, box and lever have no common parent except for LabVIEW object. Obviously, LabVIEW object isn't going to be able to be used as a lever. So the first rule is we're going to find a common parent, and if we don't find any common parents, well, we always end up at LabVIEW object. These two, the flathead and the house key, they do have a common parent. They have a common parent in LabVIEW object, but they have a common parent in lever first, and so that's where they go. Here's the interesting case. Flathead and nailer, they have two common parents. They have poundable and they have lever. If anybody who's forgotten, you can go look at the class hierarchy window for a moment, and we can see over here comes off of lever. So there, and pounding tools over here. So we've got two different things that both have a common parent. So between these two, we're going to get, that it's a type of tool, because that's the first parent, even though they both have lever in common. So that's not going to work. LabVIEW is always going to give preference to the class parent first when casting. So it's going to first check for a nearest class parent, and then it will check for a nearest interface parent. If it finds a class parent, great. And if you want to use the interface parent, you're going to need to do something to explicitly say, hey, go be the interface and then find the common parent of those. And remember, the two more specific node is always a no-op in all LabVIEW code. It is there for doing things like this, for eliminating coercion dots. It has no performance overhead at runtime. So you drop that in and you say, I am trying to tell LabVIEW that's where I want you to do, and now it works. For the record, if there's ever two common interfaces, you'll get a broken wire because the build array says, I don't know which one you want, and so you'd also use the casting there. All right, well, that's my G demo. Darren, do we have any questions in the forums that I should be aware of?
We do. Several people asked about how the inheritance is decided when you have multiple interfaces as parents, or a class and an interface, but I think you pretty much answered those questions in your demo just now. If anybody still has a question about that, please post it. I do have a couple of other questions though. A few people have asked about performance. They want to know about if there's any impacts on IDE or build performance in projects that use lots of classes and interfaces together.
So that's a tricky question to answer in this generic. LabVIEW 2019 and now LabVIEW 2020 both see significant improvements in the performance when building with classes. Interfaces and classes, for all intents and purposes, in load and build time are identical. They have enough in common that there's no meaningful shift there. I guess interfaces would have a little bit of advantage when you're disconnecting type defs because they don't carry data, but it's minimal. Both of them have seen significant improvements, but whether or not your particular build benefits from those improvements depends on what features you've specifically used and which features, which options you've selected in the app builder options. So it's faster, it's better than anything you would see in LabVIEW 2018. How much better will vary significantly user to user. If yours benefits, please, let us know and cheer on various social media. If yours doesn't, Well, we're continuing to work on it. It is a known area. It's why we've had people looking at that performance area and trying to bring that overhead down. But specifically relevant for this conversation, using interfaces does not increase over the use of classes.
Okay, another question. Do interfaces and classes have the same scoping? Is there any scoping not relevant for interfaces that is relevant for classes?
No. So classes have got 4 scopes: public, private, community, and protected. All 4 apply to interfaces equally. And those of you who are familiar with C#, C# insists on every method is 1 scope. LabVIEW allows you to pick the different scopes for the different methods. That's going to be useful when you start having these default implementations. Those of you, again, who are familiar with other programming languages, C#, Java, C++, and a lot of interface design there, default implementations for methods is really, really powerful, and it's why those other languages are adding that feature. And I've already found it quite useful in some of the G code that I've been writing. And once you have that ability to have those, the other scopes become really, really important. And so we've included those here.
Okay, next question. Do you recommend packaging interfaces separately from implementers in general?
Well, okay, so obviously not in an EXE, because you want to build all that together, and there's no reason to necessarily break it out. So this question is obviously specifically about building pack project libraries. No, there's good reason to include the implementers with an interface depending on exactly what it is you're doing. You might be providing a library of functionality that is like, select among these various various options, and you're giving your caller the ability to choose one. Well, you kind of want those all plugged in. I would never ever recommend building things in separate modules unless you need to and have a good reason to do so, because that significantly complicates your build and distribution rules, regardless of whether you're in LabVIEW or anywhere else. LabVIEW has some particular difficulties with multiple stage builds, which again we've been improving on, but anybody who's tried it knows that that can be tricky. So use it only if you need to. There's no driving reason why you have to separate those. Obviously, if you want it to be a plug-in system and you want your implementers to be independent, then yes, there's good reason to do that. And there will be some reasons to package it independent when you want to use it on a client and a server independently. And you don't want to be pulling your entire client into your server. So it's a judgment call. Look at your dependency graphs. Anybody who's a CLA and has been watching Dimitri's presentations at the CLA summits, or has found his videos online, a lot of his comments on dependency inversion will comment on, and it makes it very clear from a lot of the graphs that he'll show when it's appropriate to build those as separate modules and when not. So it's a very much an architectural design decision that you have to make, not a do it this way or not.
Okay, one more question and then we'll move on, and this is more of an administrative thing. Just so everybody knows, the same link that you used to watch this live is going to be available to watch the recording later. Stephen, I've been asked if you're going to be publishing the slides specifically at some point after the presentation.
I am. I haven't figured out exactly where yet, because this whole online NI Week tech thing has kind of messed up a lot of our usual plans for how we host these things. But I will put them up at some point, and I will be posting out on ni.com and Lava and the Twitter feed, just like I did for announcing this presentation, where those end up being located. It may not be today, but it'll be at some point next week.
Okay, great. We'll have more questions later, but why don't you continue for now?
All right. So that file extension, did anybody notice? I'm not sure you did. So we'll flip back. See that file extension sitting out there? They're all a .lv class, even my interfaces. We made a conscious decision to do this for a lot of reasons. When we first put classes out there, people had a lot of problems with adopting it. And we had a lot of advanced users say, I have figured out how to use classes, but I have a bunch of people on my team who can't use classes yet, and therefore I won't use classes. And the learning curve was fairly steep. And what we realized was we had a big breakthrough in teaching it when we started talking about a glorified cluster. And we said, think of your objects as clusters. They're not clusters. They're totally different, and they have different rules and everything else. But if you think of them as clusters and you work with them like clusters, it's a good place to start. Well, with classes and interfaces, they really are a lot closer together. And in fact, what we realized is anybody who's just using an interface and using a class, not actually writing them, doesn't care. If we look at this diagram as somebody who would be writing, somebody else has already created all these classes and things, and they use this diagram, they have a bunch of things that produce object wires, they put them together, they get a common parent, and they call some methods on it. From their point of view, there's no difference whatsoever. And we initially prototyped interfaces as being very different in the UI, and the more we put them together, the more we got the learning curve down to the point where you could add interfaces to an existing architecture that is being used by people downstream, and they never even have to know that you're using an interface. From their point of view, that's just another object. And when they click on it, they get the palette of the methods. That's a little feature we added in 2019, that shortcut palette there. So they can see what methods to call. And from their point of view, there's no difference. This object wire, the chain, there are always objects on that wire. It is exactly the same rules. So we decided, look, we're not going to do things that necessarily drive a wedge between these, and we're going to differentiate it in the places where we think the authors need to see it. That glyph there, that differentiates it in the project tree. Now, some people are going to say, well, we can't tell the difference when we're looking on disk. That's true. My contention, my hope, and this is drawing to some extent on the knowledge that we've gained looking at NXG, which combined controls and classes together into a single .g type file extension, is that that's less important, and because of the close relationship between interfaces and classes, won't actually matter in the long run. If it does, it's something we may have to revisit at some point. But that was a deliberate design decision to drive those together. There's a lot of places where we've differentiated in the UI, and there's places where we've put them together. If we look at a front panel here, pull this up. So I can drop my box class. That's an obvious class, but when I drop my lever interface, you notice the icons are very similar, but this part of the icon always comes from the private data control. Well, levers, interfaces don't have private data controls. Conveniently, because most people design the class header to be either just a bar or some glyph or something, and then the private data controls the rest of it, it's not a requirement, but it's a nice convention. You can always tell just glancing, this is an interface because it's partial icon. Now, you're just like, Stephen, that's not a language rule. I can't rely on that. I can't guarantee it. In all the years we've had classes, I've seen one violation of this, and when I pointed it out as weird, the person fixed it because they were like, yeah, that is strange. I didn't mean to do that. That's anecdotal. It's not a complete universal survey. I haven't, scientifically drilled into everything, but I see an awful lot of y'all's code. And relying on that as a convention that interfaces are partial and this is full is another part of the authors look at it and go, oh, I can see a difference, and I know that's different. But users of these things, they're like, oh, it's got a smaller icon. And it's one more place where we're able to flatten that curve. Aha, there's a COVID phrase that has taken different meaning. We've managed to bring down the learning curve by doing some of these little tricks. My hope is that in the long run, that's going to make the adoption of these much simpler than the original OO adoption was, where it took almost 10 years before we had basically ubiquitous adoption among various LabVIEW design teams. The whole discussion about why we tried to bring interfaces and classes closer together in the user interface, that's a bit of behind the scenes, why did you do that thing? For classes, in 2006, I produced LabVIEW Object-Oriented Programming, the decisions behind the design document. That was to give all of the behind the scenes, why does it work this way? Because knowing why something works is often key to using it better. I've talked on Lava about the left-handed scissors. You can hold a pair of left-handed scissors in your hand and you can cut it and you can complain to me, why did you design it? And the answer is, we designed it for your left hand. Move it over, it'll work better. And now you can come back at me and go, most of us are right-handed. Please give me a set of right-handed scissors. And that's a valid complaint. But the left-handed scissors, just knowing about it, often makes your job easier at that moment for using whatever it is at that time. And this document is designed to explain, if you're seeing something that feels awkward or doesn't quite fit your hand, maybe it's a pair of left-handed scissors. To all of the southpaws out there, this is for you. All right. So there's the shortcut URL, and Darren's going to put that in the Q&A, so you don't have to write it down. You can just copy it out. That is not a good place to learn interfaces if you're unfamiliar, because it talks about a lot of design alternatives and it kind of assumes that you already know it. The shipping documentation, I had a tech writer who was every bit as good as the original award-winning documentation for object-oriented programming. Pandang over in Shanghai is an amazing tech writer and has done a bang-up job with all of the documents. And if you go into fundamentals, object-oriented programming in the help, you'll be able to find documents that are for classes that now have new sections, new parts that are specific to interfaces, all the way through there. It covers both why and how. So why do I need to do this? What problem am I hitting? And how do I fix it in LabVIEW? And we kind of have those docs a little bit separated apart. The shipping examples are in examples / object-oriented programming. You'll find them in there. Over time, I expect to add more to the web and obviously more shipping. And there will be more things online. Now, the next part, those of you who saw some part of this presentation at the CLA Summit in September, when I got to this section on interfaces and actors, I said, yeah, I'm not going to do this. Go look at the shipping example and just know that there's no abstract messages and blah. And I just kind of blew past it. Well, today we have Alan Smith. So, Alan, let's flip over to you.
All right. Pardon me while I fiddle with the technology here. It's my first Teams meeting. Everybody can hear me okay? Give me a thumbs up if I'm good. Somebody? All right, cool, awesome. Yeah, so I am so ridiculously excited about this feature for reasons I'm about to get into. This is going to be a game changer for Actor Framework. So many things are going to get better. It was already very, very good. But as Stephen said earlier, there were some problems that we would have to solve that would simply require more work. I just got a flag, by the way, that I have bad network quality at my location. I'm broadcasting from a secret hidden bunker somewhere in the greater Austin area. So hopefully someone will flag me if there's a problem. Anyway, cool, awesome. Okay, so I'm actually going to get specific. I'm going to go look at a particular class of problem that I've been dealing with since I left NI a couple of years ago. I've gotten to get back into the job. I'm writing code again for people, which is fabulous. And I've been working on a project that gets right to the heart of this decoupling scenario. We're actually talking to about 8 different computing platforms at the same time with an actor framework system in the middle. So we're definitely dealing with cross-network coupling. And that working on that project, waiting for interfaces and having heard about them, I got the real pain point of, oh, good heavens, here's all this extra work that I'm doing. It would be so much better than with interfaces, once I get interfaces. And so I'm going to talk about that today. And as it happens, I have a demonstration. I'll be switching over here. Oh, just a second. Let me go find, here we go. Make sure I'm showing that screen. I don't think I'm showing that screen yet. Pardon me. I am clearly not a highly qualified Teams presenter, but I will get better, I promise. All right, here we go. It turns out that this exact class of problems is covered in the Actor Framework course, which I teach. And it is the case where we have two platforms that we want to talk to. We talk canonically about the desktop and a C-RIO, but it can really be anything. Anytime you're crossing an application boundary in LabVIEW where it's critically important to decouple, and we have when you take the Actor Framework course, you build up something called an evaporative cooler as the class project. And then after you've built it to run locally on a machine, we throw this curveball at you and say, great, now put the user interface somewhere else across a network. And just to show you real quick what it looks like when it runs. As you can see here, I have, to the right is the panel that would be running on my actual physical target. And then the host computer, the Windows machine, is running this really fabulous, for values of fabulous meaning dated, front panel showing the system in operation. And we built this out because this is a real thing that comes up over and over and over again. A lot of applications have to do this sort of activity. All right, I just wanted to show you what we're talking about there. And now I'm going to flip back over to my slides. Where'd it go? Pardon my fumbling. Here we go. All right. This is the system they built. There's our evaporative cooler on one side and a user interface, and they build all that out on the second day of the class. And then the third day, we say, great, stick the UI across a network. And what we would really love to do is to simply, just be very, very simple. We would like to drop in some sort of redirector, something that will take the messages going from the UI to the cooler, and instead of trying to send them to a piece of local code, actually package them up for TCP/IP transmission, send them across the network, and have the target get them. That's what we'd like to have. It should be that simple. As implemented, there is there's another actor called a network endpoint that does that work for you. So you pass your message to the network endpoint, and it just forwards it to its remote. And you can get these network endpoints online. They're available on the tools network. Lots of customers have used them. Like I said, I've got a project where I'm using them extensively. In our current, up until what I guess yesterday morning, implementation of LabVIEW 2019 and earlier, it wasn't this simple. Because a very, very sad thing that happens, which a lot of you know, if I have two LabVIEW applications and Actor Framework systems tend to be highly coupled with standard messages. The message belongs to the receiver. Okay, it's a part of the receiver's library. It invokes code on the receiver, and so they're linked together kind of permanently. But then when you go send this static message from the sender, the message gets linked statically to the sender. And so you've got this permanent coupling between the sender and the receiver, unless we do a bunch of extra work. Okay, and when you're talking about working on two application instances, it gets worse. That problem becomes really obvious how bad that problem is. Because what happens is, say, in your host project, you send a message to the target. So you pull in the target's message, now you're linked to that. The message pulls in the target actor library, and then that pulls in everything that the target actor library is connected to. And so now you have all this target code on your host side, and you've got both projects open, which you want to be because you're doing work on them. Everything gets locked. And my host is a Windows machine. My target is a C-RIO. And now I've got RT code on my Windows box, and I've got Windows code on my RT box. And so not only am I locked, everything's broken. Okay, some of this is a limitation of the LabVIEW IDE. Some of this is a limitation and some odd quirks in the way Actor Framework came together. It's just a problem that we have to solve. And we can. And in the course, we teach students how to do so. And it looks like this in all of its kind of glory. What you wind up doing is you say, okay, I have to make some decoupling happen. And so I'm going to make an interface. There's that word again. Now I've put it on this slide here in quotes because it's not a true interface. And I'm calling it specifically an interface actor because I want to differentiate between the interfaces that we now have versus what we've had to do before. Point is, this interface is a full-on actor. Okay, it is an actual, honest-to-God actor. It does everything actors do. Its methods are virtual. They don't have any implementation behind them, just like our interfaces, our ones that were coming. They exist to be targets of a message. And once I have this interface actor, now I can go make a pair of proxies. And if you're familiar with your design patterns, a proxy is a thing that pretends to be something else in your space, so you can control access to that other thing. And in this case, it's a remote proxy. We are enabling access across a network boundary while pretending to be the local thing. So the UI proxy pretends to be the user interface as far as the cooler is concerned. That's what it is. So this is very much the problem space that true interfaces are intended to solve. We have to write more code. When we do this in Actor Framework, we make now children of the interface actor that they don't add any messages, new messages typically. All they do is they implement the methods of the parent and they pull in all that dirty code, right? And the dirty code is I'm now linked to other things on my host or target side. I am pulling in code that doesn't compile on my current on a particular platform. Everything that's specific to that location, okay? And that's its job. And then, of course, our actual user interface and our actual cooler launch these proxies instead of just getting to launch the endpoints. So the proxies are also handling the code of managing the endpoints. This is kind of big, and it takes a fair amount of work to put it all together. It solves the problem quite nicely. You have really minimal coupling. The only thing that exists in both projects is the interface actor. So it solves a problem. It's great. And it's not without some benefit. And in fact, the benefit for this makes it worth doing even if you're not talking across an application boundary. It makes it worth doing just for taking my actors apart. The children of that interface actor can be anything, right? It can be my UI proxy, it can be a remote connection, it can be a local UI, it could be a test stub. In this project I'm working on, I finally got to do extensive unit testing, and being able to swap out any of these proxies for a test stub that would just collect my messages as they came in was huge in terms of my ability to be productive and work. So I've been doing these interface actors all through that project and not just across my network boundaries. But they are extra work. And it gets a little worse. By the way, what I'm talking about here is called dependency injection. If you're not familiar with the concept, it's a fabulous thing to do in your code, buys you all these wonderful benefits. But it's actually a little bit worse even than that because of the dreaded abstract message. Because the reality is that in all probability, these proxies for my remotes or for these other systems need to send messages back to their callers, which pulls an abstract message into the equation. And in the case of my remote access proxies, the abstract message is specific to one target or the other. So I don't want to put that abstract message. It has to be at the interface level because the cooler has to be able to say, hey, you thing that inherits from this interface, you get this specific message for the abstract message to send. That's going to be specific to one side of the boundary or the other. And so I don't want an abstract message intended for the cooler to appear in the interface that the UI would use, and vice versa. So that led me in this project of mine to insert another inheritance layer, which was my local proxy interface, which handled all of the abstract message component of whatever my UI proxy in this case needed to do. Okay, and that was the complete solution. And if you go and you do an artifact count of what it takes to make this go, and it works well, it solves a problem. I saw lots of benefits, not least of which was my projects load faster because I'm not doing a lot of churn behind the scenes. But the cost is a lot more code. There are 5 extra actors if you look at both sides of the equation. There are 5 extra actors. There's the interface actor. There are my 2 local proxy interfaces to manage my abstract messages, and then the proxies themselves. Each proxy implements a complete set of the messages in the interface. So there's a whole bunch more methods that have to be touched when something changes, okay? And of course, when you get right down to it, we're back to that original problem. Every single message in the proxies is essentially duplicating something that exists in either in the caller somewhere, because these are just message forwarders. I get a message from I have a VI that exists to get a message from the remote and send it to my caller, or a VI that exists to handle a message from my caller to send to the remote. So this is, from a design perspective, from a how does the system supposed to work, this is completely redundant code that exists simply to be able to take this stuff apart. It's really heavyweight for what I needed to do. I'm going to flip back to my slide deck, or not my demo, excuse me. And I want to show you within this original project some of these artifacts, just to kind of impress upon you how extensive this is. Here's what a message chain looks like. Okay, I'm starting on the host side, which is my UI side, and the user he wants to change the desired temperature of the room, and so that kicks off a message. The message is right here, and it is the message to the cooler interface set limits message. Okay, I got to cheat just a little bit here because the cooler inherits directly from this interface. Because it's just user interface. Because it's just a UI, it's just display, I was able to cheat a little bit and take one of those layers out. But I want to emphasize that I cheated a little bit. I took a shortcut on the design. Okay, so message goes out the door. Flip over to the other project. Okay, it gets received. The message gets received by this remote front panel is that proxy. Okay, the message gets received. This is an entire extra VI that exists just to recast the message up to my cooler. Okay, now again, here I'm cheating a little bit because this should be an abstract message to my caller. I chose not to be because in the course, it's early enough in the course, they just got hit with abstract messages, and I'm trying not to overload them because abstract messages are a hard concept for a lot of people. So I cheated on this project. So yes, I picked up a little efficiency here because I undermined my own design intent. That's a bad place to be. I shouldn't have to make a choice between good design and not having crazy amounts of code. Okay, but I did that. So that's like 3 steps, could have been 4 plus an abstract message just to get data across this network boundary. The one benefit that I get out of the deal, again, is dependency injection. This is the VI that launches a user interface or anything else of that matter. Anything that inherits from cooler interface can be launched by launch nested actor in this case, and so I have the ability to swap components out, which is is what we want. So let me show you now. So are you all confused yet? I mean, have we all seen like entirely too much code going on for what should be a pretty simple operation? If this were a live demo, I would be seeing nods in everybody's faces. I hope. I will assume they're there. This is so weird. All right, let me pull up now. This is I call this the minimalist solution for reasons I will make clear in just a moment. But the minimalist solution implemented in 2020 with interfaces. I am working with a LabVIEW beta. I don't earlier beta. I don't have the current version online. If anything weird happens, it's me, not LabVIEW 2020. But let's go ahead and look at the same message chain, the same operation in this minimalist view with interfaces. Okay, send the message. This looks just the same because I took that shortcut, but it's not a shortcut here. This is just the way you do it. I'm launching my nested endpoint here directly, and there we go. Note that this is a different VI though. This is actually intended for the cooler. You know, the cooler has an interface attached to it. So here's the cooler, and it implements this level control interface. Coolers inherit from level controls, and therefore they get, because of that inheritance, they also get to use the same interface. So I'm not sending the message of some intermediate actor. I'm sending the direct message, okay, which is a beautiful thing. And then if I flip back over to, again, the other project, okay, here's where it shows up at level control, and it's handled directly. So that's 2 whole steps that I took out of it because I have the interfaces, because I can use them. The key to all this, of course, being that a network endpoint handles any message. It's just a forwarder. That's all it does. And the interfaces let me do that. They let me have a forwarder that's just a forwarder. The other key change is that instead of launching the proxy and intermediary, I'm launching my actual forwarder instead, and I'm launching that directly. So that's a key change. And that's actually why I call this the minimalist solution, because I'm not being specific or particularly discriminating about the behavior of the actor that I'm launching, except insofar that it's a message forwarder. It has to be an actor. That's it. That's all I need here. So I do call that the minimalist solution. And flipping back to my slides again, I call it the minimalist solution. This is what it is. This is what it looks like. There is an interface for the UI that is the specific UI stuff. There's an interface for the cooler. That's that level control interface. I showed that to you briefly. And all there is between them are the nested endpoints. So yeah, that's. But I call it the minimalist solution because, like I say, I've discarded. In this scenario, I have discarded the one thing that was useful about all that code that I wrote before. And that is that ability to say, I'm going to put anything in this slot, in this UI proxy slot. I'm going to put anything that I want there, as long as it's something that can handle a specific set of messages. Okay, I want that functionality. Rarely, I think, am I going to want, in an actor framework, am I going to want to be able to launch an arbitrary actor. And the reason is, if you send an actor a message that's not written to handle, the actor's going to throw an error and most likely stop. And so that's undesirable behavior. I want to insist that the actor that I launch at this point in my code is an actor that will handle the messages that I expect to send it. And the UI proxy gave me that. But the interface is still a win here for another reason that I think Stephen really hit on, but we'll see it in play here again. All of my proxies throughout this other system that I'm working on with my 8 internet connections, all of those proxies have network connection code, connectivity code. That code is, how to do a TCP/IP connection. They're all wrapped up around network endpoints, but they also, in addition, have reconnect code behind them. So if a connection fails, they will attempt to listen to or initiate a connection again. And that code, that's common across all 8 of my connections here. So that's what I want to do. I want to be able to use that over and over and over again. But to do good dependency injection, I'm required to inherit the message structure instead. And the dependency injection was so valuable because the whole life of this project, I was swapping out for local simulators, things that would pretend to be the remote that I was talking to, or remote simulators. I would talk across the network to something remotely that was a simulator, or test stubs. I made the very painful decision that I was going to prioritize testability. And so I inherited based on the message. And the cost of doing that was that now I couldn't inherit from the connection code And I had to replicate that connection code across 8 different actors, actually 16 because of all the simulators. And that was painful. It was the right call, but it cost me. Now, I could have said, sure, I'm going to inherit from nested endpoints, and I'm going to make that an interface actor that has my launch code, already inherits my launching code and has these messages. I could have done that, but then everything that I plugged into that slot would pull in this network connectivity code, and that wasn't appropriate for most of what I wanted to plug in there. So I had to make this very, very painful choice because I wanted essentially multiple inheritance, and interfaces give me that. It's not a hard choice anymore. The answer winds up looking like this. It is exactly what Stephen talked about. So I do still have a UI proxy. I do actually introduce that little actor again, but it is little. All it does is inherit. It inherits directly from, in this application, from my nested endpoint. So it gets all that behavior, just does it. Okay. It implements, in the case I'm showing you here, implements the panel interface. So it gets that message set for free. And because it's a nested endpoint, it's just a redirector. So I went and disabled the need to override all of the interface messages. Okay, and I put in just enough code to do the connection, and it was truly awesome. Let me show you that. Switching my screen again. This guy. Let me close out the minimalist solution. And there's a time for the minimalist solution. I mean, it's why I took the time to show it. It's not just a handy demo to illustrate how powerful the concept is. There are times when inheriting from the actor type is the right thing to do. And there are times when you'll want to enforce the message. I tend to think you'll want to enforce the message more, but that's, we're new to interfaces, so we'll find out. Yes. So on the target side under the UI, you can see I still have, here's the panel interface, right? Remote front panel implements this interface. It has a single VI in it. That single VI is the launching code to actually establish the connection. And that's it. That was a couple of mouse clicks and moving a little bit of code around, which was a trivial thing to do. The overall overhead, the maintenance overhead on this is vastly improved. One of the goals of architecture is to minimize maintenance, and this does it for us. This makes my life so much better. I wish I could port my other project to 2020 right now, but I can't do it. I think there was another key takeaway I wanted to show you on this guy, which is that, so yeah, I moved this code from the caller, so now the caller doesn't know anything about the proxy, about what it actually does. We are strictly typed again. We are strictly typed to the interface. You must accept panel actor messages in order to be launched, because we don't have a good way of saying, you must have this set of interfaces and you must also be this type of actor. We don't have a great way to do that. Stephen can say more about why that's true. I do a cast here just to make sure that what I got there is in fact an actor and not just something that implements the interface. That's a small thing to have to do and trivial thing to have to do. So this is so much better than what we've had to do up to now. Oh, I lost my screen. Where'd it go? Let me get back to my slides. No. Sorry, guys. Having just a little bit of technical trouble on my end. Can't find the thing that I need to find. I might have stopped this. Did I? May have stopped it. I did. Okay. Can you all see? You all see my slides again? Stephen gives me a thumbs up if we can. Great. Okay. Cool. Teams neophyte. My apologies. I wanted to put this slide back up, and I mean, this is it. This is honestly my initial impression is this is how I'm going to be writing pretty much all of my actor interconnections going forward. I think this does everything that I want to do with quibbles so small as to be irrelevant. This is going to change what we do in actor framework. I plan to say more on that. Hopefully at GDevCon when it happens, I'm going to be saying more about what I think this is going to do for our actor code. It's beautiful. I'm really excited to get started with working with this. And I think at this point I'm done. And so anybody who wants to get in touch with me, I know Stephen's pretty easy to find. Some of you guys may not know where I am. You can find me on LinkedIn. You can find me on the forums. It's just ACS. And I have a Vimeo channel with some of my older presentations called Ready on the Wire. And I'm going to go ahead and relinquish sharing now, and we can take questions.
So yeah, there were a couple questions, Alan, on your content, although this first one may be for me and Stephen. I don't remember, did we add any shipping examples in 2020 for Actor Framework plus interfaces? Stephen, you're muted right now.
Yes, we did. It's in the same folder as the others.
Okay. And then another question, are there any future plans to subclass actor enqueuers to describe the interfaces supported by the actors they reference?
I encourage you as an exercise to walk through actually on paper what that would look like, and you will rapidly discover that interfaces can't do that. It is a type problem. What we want is an enqueuer that says, here are the types of messages I can accept. And that turns out to be a higher level problem of type calculus than interfaces can address. Interfaces are additive, that's multiplicative, to put it in the calculus notation. That's going to require a major significant language advance, and one that very few other languages I've ever seen can actually handle. But I really want it, so we'll classify that as research is in progress.
Okay, another more general question. Are there any changes to actor framework code in LabVIEW 2020?
Not the hierarchy, no. The project functionality that scripts them, yes. Obviously, Alan just was demonstrating the ability to generate messages from interfaces. Trying to think, I'm scanning through. I believe that we might have fixed a bug or two at some point over the length of it, but I can't recall anything that we had to do in this release.
Okay, another question. This one's more generally on interfaces. Are interfaces related in some way to Piotr's posts on LinkedIn about solid principles? I actually don't know what posts they're referring to. I wondered if you or Alan knew.
Yes. So just about anything, anytime you do a solid presentation, and for G, we always hit the D, dependency inversion, and we go, and yeah, we should do that. With about that head gesture. There are ways that we've been able to make it work, but interfaces directly go after the D, and I don't know exactly which post, because Piotr has had a number of them, but he's directly talked about it, and yes, interfaces are meant to go after that use case. In fact, as you can see on my screen that I'm sharing right now, interfaces decouple modules and inherit and enable dependency inversion, the D in solid.
All right, here's a question for Alan. Can you go over again how you define actor messages to be part of an interface?
Oh, sure. That is a trivial thing to do. Bring my screen back up. Here we go. Everything here already has messages defined, but it is, close one of my panels here. It's simple. I mean, the actor framework, this is what Stephen was talking about. You make an interface, you add a message to it. Here, I'll do a blank project.
So that menu option doesn't show up in a blank project unless you've added at least one actor into your system.
Okay, well, that's good to know. So I'll just do it right here then.
Yeah.
If I made a new interface, we'll call it Bob, because all my both my grandfathers were Bob, so I tend to call generic objects Bob. And we'll give Bob a new guy from dynamic dispatch. Okay, and we save that off. I don't need to give it a name. And it is that simple. Okay. I'm right now, currently the tools don't put your panel interface in, or put your interface inside of a library. I think we're probably still feeling our way through some of that.
If your class is already a part of a library, it will put the messages in the library. If it's not, then it puts them aside. Same behavior we've had for classes for a while.
Okay, right. You don't get that.
Yeah, we don't want to rename all your classes.
Right. We don't get the library for free like you do when you're making an actor. But yeah, right. that's a you make a library, put an interface in it, give it a method, and then just make the message. The tooling supports it.
Okay, another question that we got earlier. Are there style guidelines for interfaces, naming conventions, structure on disk, etc.? Yes.
So those of you who are familiar with other programming languages know that they often have the convention of starting with a capital I. We don't do that. I would really like to discourage anybody from using the capital I notation. For one thing, it doesn't translate into other foreign languages. And one of the nice parts of graphical code is we try to make it, we can distribute these things and share them around. For another, the I is honestly kind of a burden on refactoring in text languages. Without the I, you can swap in a class or an interface of the same name and you don't have to change any of your existing code. In interviews with C# and Java programmers about the utility of the I couldn't find anybody who was like, well, yeah, it's critical. And a lot of people were like, yeah, it more gets in the way of refactoring than it really serves. None of them were willing to abandon it because it was such an embedded convention that it would be weird to have one interface in an entire ecosystem that doesn't have it. But National Instruments will not be adding that to any of the interfaces we ship. And I'm encouraging customers to not use that in their own naming convention. That's obviously not something they can enforce. I did debate banning capital I as a thing you can type. That seemed a little restrictive. So it is your convention how you name things, but I personally would discourage it. It just doesn't serve any advantage. And it would be one more thing that would make the users downstream go, why is this weird capital I named on the front of my class, on the front of my interfaces, on the front of my classes from their point of view. As far as the arrangement on disk, it's identical to what we've been saying with classes. No changes to any of those recommendations. Everything for a given class interface goes in the same subdirectory. Use virtual folders to organize the methods in the class itself and to provide access scope. Don't try to reflect that in the physical disk hierarchy. This is notably different than the LabVIEW NXG recommendations, and there's good reasons for that. LabVIEW 20XX doesn't do a lot of the maintenance and handling quite enough, and it just creates a lot of churn to be physically moving files around. NXG is much more graceful about that. So for interfaces in LabVIEW 20XX, this is the recommendation that we're going with. Is the same thing we've been saying for classes.
Speaking of naming, we had a question about the wording for implementing interfaces versus subclassing interfaces. What do you have to say about that?
So there is an entire section in the decisions behind the design document on this point. We talk about parent interfaces and parent classes as two parents of the same child class, and we talk about child interfaces when they have multiple parent interfaces. We use the genealogy terminology. I tend to use the phrase implementing an interface only when I'm talking about specifically implementing an override of a method. This is different than industry standard terminology. This is a deliberate change from industry standard terminology, and it's because I believe that the industry standard terminology is going to have to change because default implementations change the whole nature of the game. And when you have an interface that has a default implementation and you have a child class that has a relationship with it and it doesn't override, it doesn't implement, what's the description of that relationship? When I tried to put the phrase class implements a interface in front of test users, I got a lot of confused looks like, well, what is the difference between implements an interface and inherits an interface? And I couldn't I couldn't give them a meaningful discriminator, nor could anyone else who defends the use of the phrase implements an interface. So none of the LabVIEW documentation even gets into all of this differentiation. It's only for people who are coming to us from other languages who are possibly surprised by this, and that's why the decisions behind the design document talks about it. With LabVIEW classes, I made the decision that we are going to say static dispatch and dynamic dispatch because virtual instruments was dumb. And for similar reasons, there are times when we've gone, this is the industry standard, we should cling to it. And there are times when you're like, this is not what G should be doing. It's my job as a designer and my team and backing with all of my people who help with user studies and surveying customers and all of the people across the thing. But this is one decision that landed at my desk personally, and so, but I think it's a better terminology, and so that's why we went with it. It certainly has helped a lot when we've tried to teach people classes to use that terminology, and it definitely helped with localization because base class and super class don't localize well. So there you go.
So another question. When you were talking about how style guidelines for interfaces are similar to those for class, where are the style guidelines for classes published?
They're in, there's shipping documentation that talks about a recommendation. There isn't a coherent single place for all style things, but when you create a method, we talk about where do you save it and recommending the same directory. When we talk about customizing wire appearances, we talk about not having too many of them and doing it only for key types, things like that. So I don't know that we've ever produced a single document. Now, I think that the LabVIEW Style Guide has things specific for classes explicitly in it, if my memory serves, but I can't recall offhand.
Okay. If I'm working with,
if it doesn't, that's a question for Darren Nattinger, the other guy talking.
Yeah, I'll look into that. Okay, so let's say I am working with an interface and I find myself wanting to add private data to it. What does that say about me and my current code design?
Well, it says that you're probably thinking a little too much about one particular implementation. And how is it going to get its job done, instead of thinking solely, what tasks does my caller need me to be able to do? As soon as you start thinking about, oh, I'm going to need to store this state, or I'm going to need to do this transition, you're into implementation details that you may want to have a default implementation class. It is very common to have an interface that this is the generic, and 90% of people need this specific implementation, so I'm going to ship that implementation. And that private data goes into that. That's a common pattern. But if you're asking yourselves and you're finding yourselves defining state transitions, you've strayed into the land of implementation, and you should back away and go, my customer, my caller doesn't need to know how I do the job. They need to know what job I do, and that's what goes in the interface, and only that. Okay.
Are there any visualization changes in the class hierarchy window regarding interface inheritance, and should there be, like dashed lines in UML?
Right. There are not currently. The should is a question that came up, and I kind of decided to punt. I was like, do I need it in version 1.0? No, not necessarily. Obviously, we need to reflect the class hierarchy and the interface relationships, but decisions about how to reflect it, that's straight into that area of what should be there when someone's using a class versus when someone's an author of a class. Well, that's one of the few areas where both users are looking at the same screen. There was a request in the beta forums, specifically, can I filter out interfaces? And I decided to punt on all of that and say, let's put it out there. Let's see what feedback we get. Maybe we need two separate views of the hierarchy window, one for authors and one for users. Maybe we can do it all in one view. Maybe there's specialized notation that can be toggled. I felt we didn't have enough user experience from either from customer interviews or from the beta program to be able to answer any of that. And so I said, That's an easy one. Agile, kick it to the next version, and we'll cycle it through.
All right, I have a specific question about your pry bar example.
Okay.
So a slotted screwdriver and a pry bar can both pry, but I probably wouldn't put a length parameter in the screwdriver's data generally. Like that's not something you need for a screwdriver usually. So in this case, I would want data specific to the interface for prying. Is this type of thing going to lead me to throwing more things into the private data of my class to facilitate interface methods, or is there a better way to do this?
No, it will lead you to putting more information into your class, because what you have said is that this class has this functionality that now matters. I have some interesting comments along these lines, not this specific question, but along these lines in the actual shipping example that you guys can read later of the problems with the rotation class itself. But if we accept that the hierarchy that's there is a well-formed hierarchy, yes, you're saying I'm going to implement more behavior on this screwdriver, and therefore I need to encode the states necessary to handle that behavior. That is both necessary and completely appropriate. It is why we have that separation of concerns. You could say, well, now what you really should have is multiple inheritance, and you should have something that carries around a link that you can also fold in. That is a valid argument, but having a second common parent runs into other problems that multiple inheritance has had difficulties dealing with. We looked at something, Scala traits, thanks to Dimitri's request. And you can read more about that in the decisions document. The approaches of trying to centralize the definition of private data is kind of problematic in a lot of senses. So yes, this is me speaking as an architect, and other good architects may dispute with me and not be wrong. But my opinion is yes, that is completely appropriate when you add new behavior to a class to add the private data that supports that behavior. Okay,
it's after 11:30. We should probably be wrapping this thing up.
We should be. Yeah, we just hit 11:31. I did post it into the Q&A. I posted a link to a particular forum in the forums.ni.com for follow-up questions. Alan and I will be monitoring that, and I'll leave that forum open for a couple weeks for people who see this recorded presentation. And that, I think, concludes it. Do you have any final comments, Alan?
Just that I'm really excited to get this and trying to figure out when I can compel my customers to move to 2020. I've already got one who's willing to do it, and just really excited to get to play with this. I think it's gonna be a game changer.
In that case, knowers of English, go forth and code.
Hey.
Good day.
Good day.